All right, welcome back to The Explainer. Today, we are going to crack open a real classic, a coding challenge that's pretty much a rite of passage for any developer.
So how can one simple puzzle define a developer's career? Well, believe it or not, it can. We're about to explore way more than just the solution to a problem. We're going to get into a core mindset, a way of thinking that really separates the beginners from the pros. Okay, so here's our game plan. First, we'll break down the two-sum challenge itself. Then, we'll look at the obvious solution, the brute force method. After that, we'll need a way to measure speed, so we'll touch on that. Then comes the smarter way, using hash maps. We'll compare the two head-to-head, and finally, we'll talk about why this simple puzzle teaches us so much about algorithmic thinking.
All right, Section 1, the two-sum challenge. First things first, let's make sure we're all on the same page about what we're actually trying to solve here. So the setup sounds pretty straightforward, right? You're given a list of numbers, and you're also given a target value. Your mission, should you choose to accept it, is to find the two numbers in that list that add up perfectly to that target. Let's look at an example. If our list is 2, 7, 11, 15, and our target is 9, you can probably spot it right away. Yeah, it's the 2 and the 7. 2 plus 7 equals 9. Simple enough.
But wait, there's a little twist, and this is super important. The problem doesn't want the numbers themselves, so we're not returning 2 and 7. It wants their indices. Think of indices as just the address or the position of each number in the list. And in programming, we always start counting from 0. So for our list, 2 is at index 0, and 7 is at index 1. That means the correct answer we need to give back is 0, 1.
Okay, let's move on. Section 2, brute force, the obvious way. So you've got the problem. What's the first thing that pops into your head? How would you just muscle your way through it?
Well, for most of us, the most intuitive approach is to just try everything. Literally, check every single possible combination. In the coding world, we call this the brute force method.
And here's how that would work. You'd start with the very first number, the 2. Then you'd add it to every other number in the list. Is 2 plus 7 our target? Yep. But if it wasn't, you'd try 2 plus 11, then 2 plus 15. If none of those worked, you'd move on to the next number, 7, and do the same thing. 7 plus 11, 7 plus 15. You just keep going like that until, boom, you find a pair that hits the target. Now this totally works, right? For a tiny list like ours, it's instant. But what if that list didn't have 4 numbers? What if it had 1,000,000? Suddenly, checking every pair becomes a massive, massive job. It would be incredibly, painfully slow. So that brings us to a really important idea. How do we even talk about how fast or slow an algorithm is? This is where we get into measuring an algorithm's speed. To really understand why it's slow, we need a standardized way to measure this stuff. In computer science, we have this amazing tool called Big O notation. It's basically a way to describe how the runtime of an algorithm scales up as the size of the input gets bigger and bigger. So, that brute force method we just talked about, it has a time complexity of O of n squared, or O of n squared. All that really means is that if you double the size of your list, the time it takes to run doesn't just double, it quadruples. The number of steps grows exponentially, and that is just not sustainable for large data sets.
So this is the crucial question, right? This is where the real problem solving begins. Can we do better than O of n squared? Is there a faster way?
The answer is a big, resounding yes, and it involves using a really clever tool from our programming toolbox. It's called a hash map. You can think of it as a special kind of data structure that stores information in key value pairs. The most important thing to know about it is that it's designed for one thing above all else: incredibly fast lookups.
I absolutely love this quote from one of our sources because it's the perfect analogy. Dr. Amir Charkey says, "I am creating a really good address book that tells me who is who in the zoo." And that's exactly what a hash map is for our numbers, a super fast address book.
So how does this address book help us? Well, the strategy completely changes. First, you create an empty address book. Then, you only go through the list of numbers one single time. For each number, you ask yourself a simple question. What number do I need to add to this to get my target? We'll call that the complement. Then, you just look up that complement in your address book. Is it there? If it is, boom, you've found your pair. You're done. And if it's not there, you just add the current number and its index, its address, to the book and move on to the next one. Okay, let's put these two approaches head to head. The brute force way versus the smart hash map way. Let's see how they stack up. And here it is, side by side. The difference is just night and day. In terms of time, brute force is O of n squared, which is slow. The hash map approach is O of n, which is lightning fast. How does it work? Brute force checks every single pair. The hash map? Just one pass through the list with a quick lookup. Now, there is a trade-off. See that bottom row? Space. The hash map uses a little bit of extra memory to build that address book, while the brute force method doesn't.
And this right here is one of the most fundamental concepts in all of computer science. We used a little bit of memory, a little bit of space, to save a massive amount of time. It's called a time-space trade-off.
So what's the big lesson here? What does this little puzzle really teach us? This is about more than just finding two numbers.
Really, it boils down to a few key ideas. First, the most obvious solution, the one you think of first, isn't always the best one. Second, understanding these trade-offs, like time versus space, is absolutely critical for writing good code. Third, choosing the right data structure, in our case the hash map, can make a world of difference. All of this is the essence of what we call algorithmic thinking.
So this really isn't just about a coding interview question. It's a whole mindset. It's a way of looking at problems and finding elegant, efficient solutions. So the real question to leave you with is, what problem in your own world will you solve by making that smart trade of space for time?